Okay, so welcome everybody to this exciting event as part of the Cambridge Festival. It's my great pleasure to introduce my colleague, Dr. Henry Shevlin. But before I do that, two quick things to note. Firstly, closed captions will be available during the talk. You should see a thing at the bottom of your screen now to enable you to turn them on. Secondly, after the talk, we will have a bit of time for Q&A. But if a question occurs to you during the talk, there's no need to wait until the end. You can just go straight ahead and type your question into the Q&A, and we'll do our best to get to as many questions as we can at the end. So our speaker today, Henry Shevlin, is a senior research fellow at the LCFI. The LCFI is an interdisciplinary research centre dedicated to getting the best out of the opportunities presented by current and future artificial intelligence. It's home to scholars from history, philosophy, law, computer science, and many more disciplines. And Henry is a philosopher of cognitive science. His work focuses on non-human minds, and his special interests include consciousness, suffering, and creativity. And he is also part of the team that's going to be leading CFI's new master's program in AI ethics and society. Henry's going to be giving us a talk today called From Bees to Bots, Exploring the Space of Possible Minds. So Henry, take it away.
Thank you very much, Ali, and thanks for that great introduction. Yeah, so as Ali mentioned, my interests as a philosopher are really about non-human minds in general. And I think everyone who's been paying attention will have realized that we are in an age of rapidly expanding artificial intelligence. And it's reaching the point where the gap between, on the one hand, the computational tools we've been familiar with for several decades now are starting to get a little bit closer to the kinds of minds we see among animals. And today I'm going to be talking about some of the similarities and differences between the kind of emerging paradigms we have in artificial intelligence and the more familiar minds we know in the form of dogs, cats, bees, birds, and so on. So unless you've been living under a rock for the last 10 years, you'll realize that AI is rapidly expanding in all areas of our life, from the recommendations we get on online shopping and from our search engines to medicine and business and so many other areas, Google Translate. And one thing that's probably worth flagging at the outset is there is really no established consensus definition as to exactly what defines artificial intelligence, as opposed to more familiar computational tools. And I think we're all pretty confident that something like a calculator or Microsoft Paint isn't artificial intelligence. And it's easy to say with some confidence that the kind of stuff being produced by DeepMind is artificial intelligence. But exactly where computational tools fade over into AI is much harder to define. Things like machine learning as disciplines are obviously critical for artificial intelligence. But even there, some of the simpler algorithms used in machine learning are really just an aspect of statistics that have been with us for far longer in some cases than computers have been with us. So there's no easy dividing line between a sophisticated computer and a dedicated AI. I think one vague heuristic, one vague tool you could use to think about this is just to think about different kinds of tool that we use in other domains. So think about something like a hammer. A hammer is basically what you get out of a hammer is what you put in. There's no danger of the hammer running out of control or smashing things up without your input. We use hammers very deliberately, same with screwdrivers and so on. But then as you start to add more power to the tool, say a jackhammer, then risks of things like the jackhammer running out of control or even operating autonomously, if someone plugs it in and doesn't realize that it's meant to be active, then these sorts of risks start to make a bit more sense. And I think this is probably a useful way of thinking about AI, something that emerges slowly from standard computational tools. As we give systems more power, more autonomy, more complexity, and we rely on them to do more things, the risks associated with that become greater. And that's something I'm going to touch on today. So it's probably worth starting by talking about really what's happened in the last 10 years, or rather the state of AI before the revolutions of the last 10 years. So one phenomenon that's sort of dogged AI from the outset is the cycle of AI winters, as they're called. So AI really was already something people were thinking about in the wake of the Second World War. Alan Turing famously had some very prescient ideas about AI. And since then, we've had several sequences where AI has exploded again as a research discipline, and people have been convinced that huge advances are just around the corner. And very often this cycle of hype then turns into a cycle of disappointment as people realize, oh, the things we were promised aren't going to happen anytime soon, and the funding dries up. Now, I think for reasons that maybe we'll cover later in this talk, I think we may well have broken the cycle at this point. The sheer amount of investment and sheer amount of profit coming from commercial applications of AI already does suggest to me that this time is different. But it's one reason I think that AI, until 10 years ago, say, wasn't necessarily quite at the forefront of people's imagination. Another issue with AI, again, until about 10 years ago, was is something called Moravec's paradox, or at least this is a useful way of thinking about the state of AI 10 years ago. So this is a phenomenon noticed by a computer scientist called Hans Moravec, who said that it's comparatively easy to make computers exhibit adult-level performance on intelligence tests or playing checkers, and difficult or impossible to give them the skills of a one-year-old when it comes to perception and mobility. So hopefully that sort of speaks for itself, but the kind of broader, crude idea here is that very often what's easy for AI, playing checkers or playing chess or doing arithmetic or logic problems, is the stuff that's very hard for humans, that we acquire. These are the skills we acquire later in life. By contrast, what's easy for humans, for toddlers even, and animals, non-human animals, is very often hard for AI. Things like walking across the room without falling over is a perennial challenge in any kind of AI-based robotics. And until fairly recently, a lot of other things that are quite easy for humans, things like image recognition, being able to say whether a picture is a picture of Barack Obama, or a dishwasher, or a dog, being able to identify images was still a really hard problem. Also very difficult were any kind of incomplete information games. So chess is what's considered a complete information game. Both players can see the whole board position. But something like poker, where you don't know what the other person is, what cards the other players are holding, that's an incomplete information game. And that requires a lot more inference and strategy. And again, that was very hard for AI. Machine translation, again, something that was very difficult for AI. Machine translation is an interesting case because it's been around for a long time. In the Cold War, it was a source of major interest. The US government as early as the 60s was very interested in finding ways to automate translation of Russian into English and so on. But this proved pretty challenging. One story that's probably not true is someone suggested, someone gave this example of a translation error from English, "The spirit is willing, but the flesh is weak," from the Bible, which apocryphally got translated into Russian as, "The vodka is available, but the meat is rotten." I'm sure that's not true exactly, but it gives you an idea of the kind of errors that machine translation systems were putting out until very recently. Then things started to change around 2010 with the emergence of modern systems, in particular deep learning systems, as they're sometimes called. It's probably worth flagging that these weren't actually, in most cases, dramatic innovations in how we do AI, but rather a series of incremental advances that started to pay dividends, along with a couple of ingenious leaps here and there. So these dramatic advances started to make themselves manifest in a few ways. One example that some of you may be familiar with is AlphaGo's defeat of Lee Sedol in a Go tournament in 2016. Go being a game that's sometimes compared to chess, but it's originally a Chinese game, and it's a lot more complex than chess. The sheer number of board positions makes it very difficult to process in the same kind of ways that chess computers had traditionally worked. And even a year before AlphaGo's victory, it was estimated that it would take another decade before computers could seriously take on top humans. But then, defeating everyone's predictions, AlphaGo managed to beat a world champion the following year. We've seen similar dramatic successes with AlphaStar, which is a StarCraft system, for like StarCraft being obviously a popular computer game, and it's an incomplete information game. You don't see what the other player is seeing. And AlphaStar is now ranked up there with the very top humans. Other systems like GPT-2 and GPT-3, I'll say a bit more about these, but these are basically sort of like chatbots. They're large language models, and they have incredible ability to capture accurate forms of human communication, whether it's writing poetry or Harry Potter fan fiction. And also, some of you may have seen the "This X Does Not Exist" sites. If you type into your browser now www.thispersondoesnotexist.com, you'll see an image of a person that's been generated, a photorealistic image of a person who doesn't exist, who's been generated by AI tools. So these are some of the kinds of advances, some of the feats that have been dramatically presented to us in the last 10 years. On a maybe less dramatic but equally impressive note, a lot of key benchmarks. So industry tests for AI, things like ImageNet, which is an image categorization test, GLUE, which is a natural language test, have seen some major advances. So do these advances mean that Moravec's paradox is over, that AI can now do all the stuff that's easy for humans? I think here the answer is still no. And this is easy to see when we compare AI with animals. So animals have a number of skills that AI still doesn't come close to exhibiting. Animals are most obviously self-sufficient. Animals look after themselves in the natural environment. AIs are still very reliant on humans. Animals exhibit fine-grained sensory motor control, whether it's a hummingbird drinking nectar from a flower, or an eagle catching a sparrow from in midair. Animals can do things with their bodies and their senses that are still way outside the capacity of current AI. Animals effortlessly navigate complex environments, from deserts and rainforests to tundra, full of all sorts of predators and prey. Again, this is something that is still really challenging for AIs. Trying to program a robot to navigate even a home environment is a daunting challenge. Animals integrate inputs across lots of different senses, from sight, sound, touch, smell, combining these into an accurate model of the world. And they also manage multiple competing needs: hunger, thirst, body temperature, mating, shelter, hiding from predators, hunting prey. They have a complex set of things they need to take care of. And again, AI is nowhere close to that point. And finally, animals are able to adapt to variable conditions, whether it's times of plenty or times of famine, changing climates, changing environments due to human encroachment. Obviously, these do sometimes prove challenging for animals, but the ability of animals to adapt is striking. Anyone who's seen an urban fox can get a striking example of that. This is not the fox's natural environment, but they're doing just fine. So one tool here that I think might be useful for thinking about, for further exploring this idea of how AI is compared to animals, is this idea of the fox and the hedgehog. This is a famous distinction drawn by Isaiah Berlin, a philosopher in the 1960s, I believe. And it's a bit simplistic, but roughly the idea is that you have this idea of a fox who knows lots of things. Foxes have lots of different ways of catching prey, lots of different ways of getting their food, whether it's scavenging, hunting different kinds of animals, rummaging in human bins. And whereas by contrast, the hedgehog has a relatively simple strategy for survival. If ever it's threatened, it just rolls up into a ball. Now, I think this is a bit unfair on hedgehogs. Hedgehogs are actually very smart and very varied creatures with lots of different tools. But the core idea is, on the one hand, you have some one way of getting by in the world, which is being able to do lots of things. Another way of getting by, which is being able to do one thing, but doing it really well. And I think most AI can be usefully thought of as being at the hedgehog stage. Most of the AI applications we have, the AI tools, are very good at doing one thing very well, whether that's machine translation or playing Go or playing StarCraft. So another way of putting that is to say that AI has specialized intelligence, but not general intelligence. By contrast, animals are foxes. They have general intelligence. They're very flexible. Even hedgehogs are foxes by this measure. They have lots of different ways of making a living and lots of different ways of coping with the world. So this is a slightly very simplistic graph, but this is maybe one way of thinking about it. So on the y-axis here, I've labeled this competence, where this is understood as your ability to perform tasks. And I'm also awarding extra points on this axis for the complexity of tasks. So you'll score more highly on the y-axis for playing chess than playing drafts, say. So over here, and over on the x-axis, we have generality, which is roughly the range and variety of different tasks you can perform. So up here, we have AlphaGo, which is brilliant at playing Go. And at least once it's been trained to play Go, not really anything else. Slightly less competent, but slightly more general is something like Google Translate, which can translate a wide range of languages and can do so almost as well as a human translator. It's not got the superhuman level performance of AlphaGo, but it's still very, very good. GPT-3, one of the language models I mentioned earlier, that can write passable poetry, can write reasonable Harry Potter fan fiction, can do a reasonable job of impersonating a famous person for an interview. That's a lot more general. It can do a lot of different things to do with language, although exclusively in the domain of language. And it can do them moderately well. You can figure out pretty quickly that you're not talking to a real person, but it can emulate human performance up to a point. But then when we move to the animal world, we find a lot more, or rather the biological world, I should say, we find much more generality. So something like bacteria have an incredible capability to cope in a wide range of environments. Bacterial cognition is actually a growing area of interest in biology and cognitive science. But suffice to say, bacteria are not one-trick ponies. They have a lot of different coping strategies to deal with different chemical environments. I'm still not awarding them too many marks for competence because they don't have that wide a variety of different things. The tasks they perform usually have fairly simple solutions, but still they can do a relatively wide range of stuff. Then you can sort of see this trajectory here. Bees, more competence, more generality, chimpanzees, and finally the most general purpose cognitive system ever that exists anywhere in the world is humans, of course, who are exemplars of both competence and generality, so we would like to think. The only one I haven't mentioned here is driverless cars, and I don't think this bullet point exists yet. I don't think we're at the stage where driverless cars are truly at the level where they can supplant human drivers. But if they ever do arrive, I think they're going to have to exhibit a high degree of both competence and generality if they're ever in a form that we can trust them to outperform humans in all conditions. So that gives you an idea of sort of the terrain of possible minds that we're considering today. So I want to talk briefly more about this generality axis. So what does it mean to be able to perform more things? What kind of ingredients go into making you a more general thinker? Well, one of them is robustness, by which I mean the ability to perform your actions, your behavioral repertoire under difficult conditions, to avoid glitching and getting stuck. Now here we have a tortoise on its back and a cat stuck up a tree. But these are pretty unusual instances. Animals don't normally get stuck. They don't normally glitch out for the simple reason that animals that did that quickly got selected against, evolutionarily speaking. Evolution has left animals consistently able to get themselves out of trouble in those situations. Another key element of generality is flexibility, being able to learn new behaviors to deal with different situations. Think again of the urban fox that's managed to cope in the artificial environments created by human civilization. And here we have a crow using a tool, an octopus using a shell. And this kind of flexibility, again, is pretty common in the animal world, particularly once we start looking at more intelligent creatures like mammals and birds and octopuses. And finally, we have this third category of that's important for general intelligence that I'm calling integration, but I really need a better word for it because it's a slightly complicated idea, but roughly the idea is animals combine lots and lots of different information from different senses. And they also have to manage lots and lots of different needs, as I mentioned earlier on, from hunger, thirst, shelter, and so on. And mating, of course, as the picture of the lions there should illustrate. We've got lots of different things that we need to do as animals, that all animals have to do. And to do that, we have to balance different needs and take information from lots of different senses. The net result of all this is that we end up with autonomous and independent creatures. So how does AI measure according to these metrics? Well, not great. AI is not particularly robust. From driverless cars that crash due to snowy weather, to machine vision systems that misclassify images due to simple deceptive filters applied, to chatbots that make non sequiturs or strange, obviously inhuman asides. AI often glitches or fails. And I think this is a problem not just with AI, but software in general. I could go on a rant here that I'm going to resist about how much buggier and glitchier software is now than 10 years ago. But suffice to say that, yeah, AI still doesn't have anything like the reliability that animals have been forced to acquire thanks to the rigors of evolutionary pressure. AI is also still not really very flexible. One problem for a lot of AIs is something called catastrophic forgetting. Roughly speaking, if you train most systems, train an AI to be able to perform one task very well, like playing Go, and then train it to perform another task, like playing chess, it will have forgotten lots, if not everything it learned about Go to begin with. Now, this is an area where people are making progress. One prominent paper from a couple of years ago is called Overcoming Catastrophic Forgetting, and we are starting to, again, make some progress in this area. But it's still fair to say that AIs don't have this kind of robust capacity to acquire lifetime skills without those skills degrading and continuing to learn new skills and new information. Likewise, AI is often very data hungry. I can tell you that the word neige means snow in French, and from that one utterance, you can go away and probably read the word neige and know that it means snow. And that one piece of information you can take away and use to memorize something forever. By contrast, AIs typically need lots and lots of examples to get there, to figure out what a particular category an image belongs to, for example. Again, this is an area where people are working hard to improve systems. One-shot learning, meaning learning from one example, or few-shot learning, learning from a few examples. These are active areas of development, but still, compared to humans and in some cases animals, AIs are still not very flexible. And finally, AI is still relatively single-minded. It doesn't display the same kind of complexity of integration that animals can display in terms of sensory motor coordination, pulling information from different senses and managing different needs. So the consequence of all this is that AI agents are still quite a long way off. Still some key advances need to be made. There are some promising advances, as I've mentioned, and I think AI is slowly becoming more and more like a biological agent. Some examples of progress being made in this domain include things like giving AIs better memory. This is a technique called episodic AI that's currently at the cutting edge. Giving AIs better understanding of causation is another important area of development. Teaching AIs not merely to sort of learn from statistical patterns, but to get a better sense of how things actually work, as well as teaching AIs to have better general learning principles. You know, we talk about things like university education as important, partly because you're teaching people to be better learners. You know, you're learning about English literature or history, but you're also learning how to learn. And there's been a similar interest in teaching AIs these general learning skills. And there are already some impressive steps towards greater generality. So GPT-3, which I mentioned before, was able to learn to play chess just based on the linguistic databases that it was, the linguistic corpuses that it was trained on. So having seen large amounts of text on the internet, it turned out that it actually acquired, from just learning about chess notation, it had acquired the skills it needed to play a passable game of chess. So that was a nice example of AI becoming more general. And there are, of course, plenty of commercial incentives for more general AI. Something like driverless cars, as I mentioned, is a case where more general AI is going to be critical, I think, for dealing with the wide variety of road conditions and unpredictable circumstances that any driverless car is going to find itself in the natural world. And so thinking now finally about the future of general intelligence, when more general AI starts to arrive, maybe in a decade or 2 decades hence, what will it be able to do? Well, potentially it could give us AIs that are more like organisms than tools, true autonomous AI agents. This might mean fully automated factories that can run themselves without any human inputs at all, or farms where every aspect of the production line process is handled completely autonomously, to the long-awaited robot butlers we've seen from science fiction and childcare providers. I think one very daunting challenge, a test for truly general AI would be a sort of nappy test. When we build robots that can that we trust to change a baby's nappy, then that'll show that we've really arrived at something more like general AI. But of course, as we move towards more general AI, there are major risks too. As you can see from our interactions with animals, when you're dealing with non-human agents, genuine agents that are genuinely autonomous, havoc can result, whether it's buffalo stampedes or plagues of locusts. And whilst it's common to think about sort of AI dangers or AI risks in terms of Terminator scenarios where some cold-blooded, malicious AI decides to exterminate humans, I think a lot of the risks that are going to emerge from more general AI are more like the examples I just mentioned, stampedes and plagues of locusts. Simple-minded, relatively simple-minded, more general or autonomous agents doing things that don't perfectly align with our own interests. In light of that, then, I think it's probably good that we still have some time to prepare before general AI gets here, and the gap between bees and bots is closed. Thank you very much for your attention, and I look forward to hearing your questions.
Okay, so thanks, Henry, for that really fascinating talk. We do have a bit of time now for questions, so if anybody has questions, go ahead and put them in the Q&A and I'll try and get to as many as we can. So the first question comes from Matthias. Matthias asks, would you say that in a nutshell, the difference between general and specific intelligence is the ability to adapt to changes in the environment, and that there are no AIs yet that can adapt to those external changes?
Yeah, I mean, I think that's a reasonable way of capturing kind of the core idea. Certainly one advantage of general intelligence is manifest in the ability to adapt to changes like that. I think things like, so that the way that's framed there is putting the emphasis on flexibility, but I think robustness is also key. Part of general intelligence is being able to be reliable in that sense across different conditions. So I mean, I guess there are two ways of thinking about being able to adapt, right? One is being able to do what you already do, but do it under different conditions. And another is being able to do new things to cope with different circumstances. So being able to sort of walk on ice might be an example of the first thing. You know, it's slightly different conditions. You want to be able to walk across the ice without falling over. Whereas doing something completely novel, say, is something more like what I think of as exhibited by the case of the fox moving into urban environments. But yeah, I think adaptability is a useful way of thinking about kind of the core idea there.
Great, thanks, Henry. So we have another question now from Janet. Janet asks, if you introduced a form of reward or punishment to AI programs, would you expect to see them then evolve at a speed that's more comparable to animals and become very competent given their processing power?
Yeah, so evolutionary algorithms have been around for quite a while. There's some interesting papers discussing sort of their strengths and weaknesses. And the idea of sort of reward and punishment is already arguably present in something like artificial reinforcement learning, which has driven a lot of the progress in the last 10 years in AI. I think it's still fair to say that the kind of complexity, both of our biological basis, DNA, and also the kind of evolutionary environments we found ourselves in, these are not things that we've been able to naturally recreate to build better AIs, would that it was so simple. But I definitely think the core idea that's driven a lot of AI progress in the last 10 years and will probably drive future AI progress, this idea of exploiting natural sort of feedback loops from reward and punishment, or similar sort of gradients driving improvements in behavior and performance is going to be part of any key solution. Yeah.
Brilliant. So another question from Steve. Do you see any value in teaching morality to AIs in the same way that in the past animals weren't considered or ascribed with morality? That position has now moved on and we treat animals in a moral way. Do you think we could say the same about AI?
Yeah, so I guess there are sort of two elements to this, right? So one is, on the one hand, we want to build moral agents. We want to build AIs that we can trust to do the right thing. The more we endow them with decision-making powers, the more we want to make sure they'll act in ways that are aligned with human interests and human values. And there's also the question of whether AIs have moral status in their own right. That's something I'm going to be talking about tomorrow. I think in regard to the first question, it's worth distinguishing between sort of making sure safeguards are in place to ensure that AIs act in ways that are both predictable and, as I say, aligned with human values. But I think that's sort of not too different from the kind of some of the ways in which we've already put restraints on existing technology. You might think about some of the limitations that you might think of, programmed into certain computers or certain vehicles to limit their operations in certain ways. There's a difference between that and building genuine artificial moral agents, things that we would trust to do general moral decision making. That latter is, I think, much further off. But I think as soon as we start to approach something like human general level intelligence, absolutely, teaching them to make sure teaching them in ways that giving them a good moral education is going to be critical. Absolutely, agree with
that. Interesting stuff. So another question comes from Vanessa. Vanessa asks, won't there always be a fundamental difference between AI and human minds unless AI somehow develops this very human characteristic of having conscious self-awareness? And what, in your opinion, is the biggest difference between AI and human beings that's going to stop them from developing that characteristic?
Yeah, so AI consciousness is a really interesting topic. It's something I've written a few papers about. There are some really big differences of opinion here, partly because consciousness is still arguably the aspect of reality that is, the aspect of everything that's still least well understood. We still fundamentally don't have a good idea of how consciousness emerges from the brain, why a bunch of neurons firing in a certain pattern should give rise to subjective experience, pleasures, pains, emotions, and so on. As long as that mystery remains, I think there are going to be open questions about AI consciousness, about artificial consciousness. My own view is that consciousness is fundamentally connected to the human brain, or not just the human brain, to brains in general, and in particular, the information processing and computational capacities of the human brain. And so I'm inclined to think that a sufficiently powerful AI with the right sort of internal organization could be conscious. Whether or not we necessarily realize that it was conscious, that's a further question, I think. And I think one concern we might have going forward, and again, I'll talk about this a bit more tomorrow, is that we might create conscious AI without realizing it. But yeah, I think it's likely that in my lifetime, conscious AI will be with us. And insofar as that will mean that AI has closed the last gap with humans, that'll be a significant moment for humanity.
Excellent. So we are just coming towards the end of our time now, but I just want to take one last question that I think is really interesting from Tom, who asks, how seriously do you take the Stephen Hawking position that AI will make humans obsolete or poses an existential threat?
Yeah, this is really, really tough. I think AI definitely can pose existential threats. In terms of technologies, AI has the potential to be the most powerful technology we've ever built. And as we move towards autonomous agents, a huge number of risks arise, whether that's just sort of out of control machines or something more significant like superintelligence that is not aligned with human interests. There are lots of very dangerous potential scenarios down the road. One thing I spend way too much time thinking about is the Fermi paradox, which is why we have not been contacted by aliens if humans are so mediocre and the planet Earth is just a typical world. Where is everyone? And one common answer to the Fermi paradox, one answer that's taken very seriously, is that civilizations destroy themselves before they reach a certain level of complexity and development to be able to go off and explore the cosmos. And AI is often mentioned as one of the existential threats that might cause species to destroy themselves. So I think I do rate that risk very high. Although I don't think it's just as simple as sort of a Terminator scenario necessarily. I think there are lots of different ways in which AI could pose dramatic threats. As to this broader idea of obsolescence, well, you might think even if we manage the transition to an AI, the true super intelligent AI successfully, you might think there would still be value in more simple modes of human existence. You think about communities even today that eschew technology, like the Amish and so on. I can imagine in the future that some people will choose to live without AI, or will choose not to be plugged into some kind of super intelligent system in the future. So hopefully, if we manage the transition towards super intelligent AI successfully, we'll be able to choose the degree to which we are willing to whether upload ourselves or otherwise be plugged into some kind of super intelligence, or prefer the more simple modes of life. Hopefully we'll still have the choice when the technology reaches that point.
Great. So thank you everybody for those fantastic questions, and sorry to those of you whose questions didn't get answered, but we have now run out of time. So it just remains to thank the Labour Hume Trust for funding our research, and the Cambridge Festival organisers and everyone who helped us to organise this event, to all of you for coming, but most of all, obviously, to Henry for a fantastic talk and some really interesting answers to those questions. So if you enjoyed this talk, which I'm sure you did, you should also come along tomorrow for another talk that Henry's giving on the moral and legal status of artificial agents. And you can find the booking details for that on Eventbrite in the same kind of place you found this one. And with that, thanks all and goodbye.
Thank you.